Dear students, in this class we are going to do some problems using the Smith chart. Already we have done so many number of problems on the transmission lines using our mathematical equations which are taking some time to solve them. But whereas if you understand the Smith chart properly, it doesn't take much more time to get the results. So already in the last class I told you the Smith chart is nothing but the intersection of two orthogonal circles. Those are nothing but the constant R circles as well as constant X circles. These circles have constructed using the circle equations, and coming to this R circles, the center is R by 1 plus R and 0 and the radius is 1 by 1 plus R. Whereas for the X circles, the center is 1 and 1 by X and the radius is 1 by X. Now for getting the complete Smith chart, you have to superimpose these R circles on these X circles. Then you are going to get the complete Smith chart. And if you understand the Smith chart properly, happily you can do so many number of problems here. So that is the reason I told about the properties of the Smith chart also. So coming for this diagram, once again I am telling you, there are three scales here. The inner one is nothing but a protractor which is telling about the angle, and this is telling about the angle of the reflection coefficient, because you know Smith chart is nothing but the graphical representation of reflection coefficient in complex plane. And the other scales are telling about the distances from generator as well as towards the load. These distances always will be given in terms of lambda here. And suppose for example, if you take the outermost circle here, this is telling about towards the generator, and it is telling 0.06 lambda, 0.012 lambda, 0.018 lambda, 0.25 lambda, again it is coming like this. But whereas the next circle, the next scale, it is telling about towards the load. It is in terms of also lambda here. But whereas the inner one is telling about your protractor, telling about the angle of the reflection coefficient here, because your reflection coefficient is having both magnitude as well as phase angle. And the most important point is, and if you complete one revolution of the chart here, that is equal to lambda by 2. So half of the wavelength. So this lambda can be calculated using your basic equation, lambda is equal to velocity by frequency here. And if you want to complete the one wavelength here, and automatically you can say it has to cover 720 degrees here, because lambda by 2 is covering 360 degrees here. So once you know this just small issues about the Smith chart, happily you can do any type of the problem within the no time. That is the reason now I would like to show you what exactly the Smith chart is. Now the given problem is a 30 meters long lossless transmission line with Z0 is equal to 50 ohms operating at 2 megahertz is terminated with the load ZL is equal to 60 plus J40. If the velocity V is equal to 0.6 times the velocity of the light on the line, find the reflection coefficient gamma, or otherwise sometimes it can be represented by K, and the second one is standing wave ratio S, and the third one is the input impedance. So very simple, this is the data given here. Load is 60 plus J40, its characteristic impedance Z0 is equal to 50 ohms. The length of the transmission line is nothing but 30 meters, and is going to calculate these three parameters: reflection coefficient, standing wave ratio, input impedance. You know very well how to calculate all these parameters using the equations. So the very first one is the reflection coefficient. So I would like to just calculate all these parameters using the mathematical equations as well as using the Smith chart also. Then you can understand how to get the values using the Smith chart within no time. So your reflection coefficient K is equal to ZR minus Z0 by ZR plus Z0. This is the basic equation of your reflection coefficient. Because your Smith chart is nothing but the graphical representation of the reflection coefficient in the complex plane. So that's why you try to calculate the reflection coefficient K, or otherwise it can be represented by gamma also. Therefore, K is equal to ZR means 60 plus J40 minus Z0 means 50 divided by 60 plus J40 plus 50. So if you simplify this, K is equal to 10 plus J40 divided by 110 plus J40. If you simplify this, it will be 0.356 at an angle 56 degrees. 56 degrees. So, like this you are going to get the value using this equation. Now, coming to the Smith chart, you know very well, my dear friends, Smith chart is nothing but the combination of two types of circles, orthogonal circles, R circles, and as well as X circles. It is an intersection of two types of circles, R circles and X circles. And in the previous class, I already told you how to construct the Smith chart also. Now, I am just showing the entire complete Smith charts to you so that you can do the problems without confusion. That is the reason always my interest is to show the entire Smith chart to you with all the details here. So, coming to this, these are the R circles and these are the X circles, and the circles above this horizontal axis is called as positive reactance circles, positive imaginary circles. Whereas the circles below this horizontal axis is nothing but negative imaginary circles, means capacitive circles. To complete one revolution around this chart means it is nothing but the coverage of lambda by 2. That means it is 360 degrees. So, lambda by 2 is corresponding to 360 degrees. If you want to complete one wavelength, that means it is 720 degrees. Okay. Now, that is the reason, if you see the Smith charts, there are some scales here. The outermost scale is telling about the distance in terms of wavelengths towards the generator. So, if you see here clearly, 0.0, okay, 0.04, 0.05, 0.06, all these things are actually given in terms of lambda. So, if you completely come to this place, it is 0.25 lambda. That means lambda by 4. Again, you have to come like this to complete another lambda by 4. That means moving around this entire chart is nothing but a coverage of lambda by 2. Exactly, the inner scale is telling about moving towards the load, that means counterclockwise direction. So, just for the ready reference, he has given the distance on the transmission line in terms of wavelengths. One scale is from towards the generator and other one is from towards the load. Just for our convenience, he has given two scales here. And the third one is, this third one, it is in terms of degrees. It is telling about the angle of reflection coefficient. The third one is angle of reflection coefficient. And the fourth one is angle of transmission coefficients here. And exactly like this, all these things are already given in the radially scaled parameters also. What are the radially scaled parameters? He has given the scales here. If you observe clearly here, they are giving the information about, the first scale is giving the information about SWR, standing wave ratio, and the second one is return loss, and the third one is reflection coefficient, and fourth one is also another reflection coefficient ERI, and in this direction means it is towards the load and it is in the towards the generator here. So now, by using this Smith chart, I would like to do this problem. So, the load impedance is here 60 plus J40, but you know very well, Smith chart is meant for normalized impedances. Normalization means dividing by the characteristic impedance. So, what is the normalized impedance here? What is your ZL? ZL is equal to 60 plus J40. So, ZL is equal to 60 plus J40. I want normalized impedance means Z small l, it is a notation I am using. So normalization means dividing by Z0. That means this is equal to ZL by Z0 divided by the characteristic impedance. So 60 by 50 because characteristic impedance is 50 plus J 40 divided by 50. This is okay. So what is this 60 by 40? I can say this is 1.2. So this is equal to Z normalized impedance is equal to 1.2 plus J. What is this? 40 by 50 means 0.8. 0.8 meter. So now listen. ZL is equal to normalized impedance is equal to 1.2 plus J into 0.8. It is a normalized impedance here. Normalized impedance. So what is an impedance? Impedance means it is an intersection of resistance circle and reactance circle. So just identify here what is the 1.2 resistance circle and this is the reactance circle. As you are having here plus J, always you have to go for the upper half. Lower half is meant for negative. Upper half is positive. So you have to know about this 1.2 resistance circle first. So what is that 1.2 here? So you can go here. These are the circles. These are the circles like this. I want 1.2 circle means this is the 1.2 circle. This is the 1.2 circle. Here it is. And one more thing is 0.8 reactance circle plus J. So where is the 0.8 here? This is 1.2. 0.8 means this is. So this is the 0.8 and this is 1.2. The intersection is nothing but the load point here. That is nothing but the intersection here. So I can say this is the intersection here. 1.2 and this is nothing but the 0.8. This is the point of your Z small l. I can say that. Normalized load impedance. Okay. Now just take a scale here, right? Take a scale and try to connect this point load impedance, normalized load impedance with your center of the circle, that is called 1.0. 1.0. So how to do this? This is 1.0 and this is nothing but your ZL like this. So I can say this is the one where you are seeing this. This is the diagram. So let it be, it is at the center. This is nothing but the center here, 0. Okay. And this is nothing but the point P here. Point P, that means the load impedance and 0. Just elongate this line toward the periphery because this is nothing but the total circle, that is called your, you see, this is the total major circle, unit circle. Within this circle only all the circles will be present. So take a long scale here and just you try to elongate this value, elongate this one. So you can say that this is equal to, right? So now you can do like this. This is the point here. This is right. So now if you do like, let it be 0 and this is a P and this is nothing but the Q where it is actually intersecting this maximum circle like this. So if you want to find out the reflection coefficient here, then try to understand this. It is the ratio of OP to OQ. That means total distance. So what is the total distance here? Measure with this total distance with your scale. So it is totally 30. This is total full scale is 30 and again, so this is the point here and you can say this is another 2 centimeters. That means this is 32 centimeters. OQ is equal to, I can say OQ is equal to 32 centimeters. And what is this OP? OP is equal to, so what is this OP? OP means I can say this is 11 centimeters. This is nothing but the 11 and exactly it will be 11.2 centimeters. So the reflection coefficient gamma is equal to OP by OQ. That is equal to 11.2 divided by 32 centimeters. Okay, that is equal to, I can say 0.350. This is the magnitude. So listen carefully. From your equations, you got the reflection coefficient K is equal to 0.356. But whereas here you got 0.350. Our Smith chart is always giving almost all the values close to the actual ones. It will be giving them sometimes approximate values also. So this is the way of doing the problem for the reflection coefficient. What you have done? You have identified the normalized load impedance. Then you have connected to this center chart here and extended toward the main circle, and you have measured the distance here. This OQ is 32 point something like centimeters and OP means 11.2 centimeters. If you take the ratio of OP to OQ, you are going to get your reflection coefficient. But friends, your reflection coefficient is not a real parameter. You know, reflection coefficient K will be having magnitude as well as phase angle. Phase angle also. You got the magnitude now. But how to get the phase angle? Phase angle means very simple. Just here, the third scale is telling about your angle of reflection coefficient. And try to identify where it is touching. It is in between 50 and 60. It is touching in between 50 and 60. It is almost close to whatever the point here, it is in between. It is nothing but 56 degrees. 56 degrees. So that's why I can say that the reflection coefficient phase angle is nothing but 56 degrees. That's why K is equal to 0.350 at an angle 56 degrees. You see how simple it is? Just putting the normalized impedance on the Smith chart is much more sufficient. You try to identify this point and try to use your scale to get the values of OP and OQ, and the ratio is nothing but reflection coefficient, and where it is touching on this one, 56 degrees. That's why my reflection coefficient gamma is equal to, or K is equal to, I can say 0.350 at an angle 56 degrees. Simple. So this is the way of calculating the reflection coefficient. The very first one is you have to identify the point on it. Once you get the reflection coefficient here, then OP as radius, draw the circle here. Draw the circle taking OP as a radius. So try to take a compass for this and do this, and definitely you are going to get the values here. So how to do this? Very simple. Take the compass here. This is, and you can say this is as a radius. So this is as a radius. You have to adjust here like this. This is the radius, and using this as a radius, draw the circle here. Draw the circle. Right. So how to draw the circle? Like this. So after getting this normalization point here, take OP as a radius and take a compass here and draw the circle like this. Once you draw the circle, identify the point of intersection of this circle with this positive real axis. And this circle is called as SWR circle, standing wave ratio circle, or reflection coefficient circle. So you have to identify the point of interaction here. This point of interaction is around, it is 2. So this will be 2.0, which is nothing but your SWR, standing wave ratio. So very simple. First, identify the normalized point on this. Plot the normalized impedance on the chart. And then just draw the line from this center of the chart, that is called OP. Extend this OP to the periphery of the chart, then it will be Q. And take the ratio of OQ to OP, it will be the reflection coefficient. And where exactly it is intersecting with this scale, that is nothing but angle of reflection coefficient, 56 degrees. So you got the information about this reflection coefficient. Once you get this reflection coefficient information, then take the OP as a radius, draw the circle. This circle is nothing but standing wave ratio circle. Identify the point where it is intersecting with this positive real axis, that is called 2.0 here. That is nothing but the standing wave ratio. So happily you can check it whether it is correct or not, because you know already reflection coefficient is calculated here. Therefore, how to calculate your S here? S is equal to, I can say, S is equal to 1 plus k divided by 1 minus k. Therefore, it is equal to 1 plus 0.356 divided by 1 minus 0.356. It is almost equal to 2 point something, 2.08 or something. This is the standing wave ratio. So, this is the way of calculating standing wave ratio and reflection coefficient using the equations as well as the SMART. But definitely friends, getting these values from the Smith chart is very easy compared to your mathematical calculations. Now, we are going to see how to calculate the third parameter he has asked here, that is nothing but the input impedance. Okay. Now, we are going to calculate the input impedance using the Smith chart. So, what is the input impedance? Input impedance Zn is equal to Z0 into ZR plus JZ0 tan beta L divided by Z0 plus JZR tan beta L. Okay, this is the expression you are using for calculating this. What is this beta L? Beta L means electrical length of a transmission line. Beta means 2 pi by lambda and L is nothing but the length of the transmission line. So now, from the given data, you have to calculate what is lambda. Lambda is nothing but, because the distances are always given in terms of lambda, but in the problem the distance is given in terms of meters. The distance is given in terms of meters. Try to convert into lambdas. So first of all, the wavelength lambda is equal to velocity by frequency. What is the velocity has given? 0.6 V0. 0.6 into V0 means 3 into 10 power 10 centimeters divided by the frequency. How much the frequency has given? 2 megahertz. So 2 into 10 to the power of mega means 6. Therefore, your lambda is equal to, see how much you are going to get here. This is 0.3. 0.9 into 10 to the power of 4. That means this will be equal to 90 meters. Lambda is equal to 90 meters. And you know very well, lambda by 2 is relating to 360 degrees. And lambda here is 90 meters. The given length is 30 meters. That means it is 1/3 of this. So you can say that this is lambda means it will be equal to 720 degrees. Whereas the given length is nothing but 30 meters, that is nothing but lambda by 3. So lambda by 3 corresponds to 720 divided by 3 means 240. 240 degrees you can say that. So you have to go for the phase angle of 240 degrees like this. So what is this 240 here? Now if you take here, so this is OP and this is the the line here. From this point you have to move towards the generator. Towards the generator means clockwise direction, because I want the input impedance here. Input impedance means whenever you are calculating the input impedance of the transmission line, you have to move from output to input side. That means you have to move towards the generator. Here in our chart, moving towards the generator means clockwise. Clockwise you have to move. So this is the point, our point is like this. So from this point I have to move like this in the clockwise direction. How many degrees I have to move? I have to move around 240 degrees. So very simple calculation I can tell you. So this is actually 0 degrees. This is already 56 degrees already given. So from this point to this point, if you come like this, it is 180. So this is the 180 plus this is 56 degrees, 136 degrees. This is 136. Okay, and is 236, and he wants 240 degrees. That means another 4 degrees means from 180 to 170 it will be 175. That means 5 degrees here. So somewhere around this you are going to get your 4 degrees here. So that point you have to just you have to join this point with the center of the chart like this. So take a scale once again here, and so what is the scale you can give, and try to do this. This is the center of this one, and you have to draw this like this, and take a bigger scale here. This is, and this is 170 to 175. That means this is the scale, and you try to do this, and this is the point here. Just you try to join like this. This is the point. This is the point like this. That means this is the actual point here. From here you are moving in the clockwise direction like this. How many degrees you have moved? 240 degrees. And that is the reason you are getting this point like this. Now identify this intersection here. This is the intersection point here. And where exactly it is? And try to identify the resistance circle. This is 0.4 and this is 0.5. Okay, 0.4 and 0.5 means it is in between. This is the R circle, 0.47 circle. This is. And if you see this reactance circle, it is like this. It is 1.0. It is 1.0, but it is very much nearer to this. It is almost all equal to 0.035 reactance circle. So what is the point here? This point can be written as 0.47, okay, plus 0.035. This is nothing but the point here. So what is this point here? Z input. Z input means this is Z small in. That means normalized input impedance. So if I want that actual impedance, what I have to do? I have to multiply with characteristic impedance. Very simple, friends. From this basic line, you have to move 240 degrees toward the generator like this, because your lambda by 3 is corresponding to 240 degrees. Then identify this point here. That point is nothing but 0.47 plus 0.035. This is nothing but the normalized impedance. Okay. So Z total input impedance, Z capital N is equal to Z naught into Z small n. That means you have to multiply with the characteristic impedance Z naught here. Therefore, what is the value you are going to get? Therefore, Zn is equal to 50 into Zin. Zin means 0.47 plus 0.035. This is. So if you calculate here, you are going to get your Zn is equal to, I can write down here, Zn is equal to, from your chart, Zn is equal to 23.5 ohms plus J into 1.75 ohms. Friends, this is from the chart. You have got it. How simple it is. From the chart you have calculated like this. Suppose if you want this input impedance using this equation, you have to just substitute ZR as well as your Z0 here. And after the calculations also, if you calculate like this, and it will be equal to your 23.9 ohms, okay, plus J you can say that 1.35 ohms. So what I mean to say is, once you are getting a practice on this Smith chart, instead of going for complex calculations, we can get the same results using the Smith chart within no time. The only thing is you have to understand what exactly the Smith chart is. So one more thing is here, once you know this reflection coefficient, you got the standing wave ratio. That means intersection of the positive real axis here. The same thing I can say, here you are having radially scaled parameters here. These are radially scaled parameters. The standing wave ratio, reflection coefficient are also given here like this. So what is the standing wave ratio we got? 2 here. This is nothing but 2.0. Now take the tangential line on this, then tangential line on this is, okay, tangential line. Then if you take the tangential line, you are going to get your standing wave ratio as well as reflection coefficient also like this, reflection coefficient. So like this also you can do this, this is, and take a tangential line onto this and then try to identify the points where they are intersecting with this axis, and almost all you are going to get your approximate value. Here you see SWR means it is almost all 2.0. So, whatever the 2.0 you got here, and the reflection coefficient is what is the reflection coefficient you got? 0.358. It is also like 0.3, 0.4 in between, it is 0.358. This is the way of understanding the Smith chart. You are going to calculate all these values using the Smith chart within no time. I hope you understood how to calculate the reflection coefficient, standing wave ratio, and the input impedance. So, if you go on doing this type of practice on the Smith chart, within no time you are going to calculate all these parameters. Okay. Thank you very much.